Hello, this is part two about my about the nature of intelligence and just learning the system. So excuse little technical glitches here. Okay, so where I finished off in part one is talked about other systems that are metamath and also intelligent systems, and I'll explain what I mean by intelligent systems. But evolution is a metamath system, meaning that it requires something outside of mathematics. So metamath, I'm just using that because we have something that is not purely mathematics that requires something outside of mathematics to function. It doesn't mean that it's better. It just means that it can't fully be what math is or mathematics is. Anyway, intelligence is a metamath system because intelligence is interactive, and that's the point of intelligence, is that you want to interact. That's what it does. So intelligence, and here's the thing, in general, a lot of people think of intelligence as just being a better version of something else. That, let's say you have a computer, get a faster, better computer, better, 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 faster, 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 and all of a sudden it becomes intelligent. No, intelligence is a different type of thing than the calculations and and functioning of a computer. You could have a computer that does have an intelligent system. It's just that it's a different type of system than mathematics, than algebra, than logic. Okay. So we have a function. Function is known and repeatable and useful, and that's what a computer is doing. It has some function. You put in numbers into that, it gets a solution to it. You put the same numbers in, it gets the same numbers out. That's why I said a random number generator would not be a true random number generator is not a mathematical function. You put in a number and you get out a different number each time. So MetaMath doesn't have these true functions. As I said, you have the structure of mathematics, but something is different there. Where we can't use a function like we're used to. So choosing a complete system, starting with a system or adding to a system, requires MetaMath. And so I talked about this with the idea of you have a complete mathematical system, that there's some choices at the beginning of a system that makes it a construct, and that you have more than one of these constructs. For instance, you have classical mechanics, and you have the mathematics required for classical mechanics, and that's a complete system that works quite well. It's just that it doesn't work when we start talking about velocities approaching the speed of light. We start talking about scales around the size of an atom. That where you have to have the quantum regime. That's when it fails. But within a certain range, it works quite well, and it's a complete system. It's really the most important point here. As a matter of fact, you could have a system um, that really doesn't that's just totally wrong as far as physics is concerned, and it could be a complete and self-consistent system that's okay with itself. It just doesn't match up to physical reality. So you choose, in a sense, you're choosing, you're constructing a system. And let's say, for instance, you have two complete systems. Choosing which one of those systems, A or B, that you need, that would be MetaMath. And that would require something that's not within that system. Both those systems are self-consistent. There's nothing there that says this system is better than the other system within that system. It's you from the outside have to pick which one to use. So classical mechanics, there's nothing in that complete classical mechanics system that says, oh, wait a minute, you have to use quantum mechanics. You need something outside that system that says, oh, you need it. At least for some things, maybe for everything. Intelligence, so MetaMath requires a goal. I have to have something that's outside of that system. Why am I choosing it? Why am I choosing this system over that system? It could be experiment that you say, both these are self-consistent systems, but this system fails for these experiments. There's nothing in that system that says it would fail for that experiment, but when you do an experiment that says that gets one answer, gets a yes in that complete system, you do the real experiment and it gets a no for that. And you say, oh, I can't use that system. It fails, even though it's a self-consistent complete system. The experiment shows me that this is not the correct system. So we need something that's a goal. I want something that matches physical reality, and that's the goal, for instance, as I was talking about. And there's other goals out there. Intelligence is a process that adds to a self-consistent system that is still consistent within that system and achieves the goal. So I can go and, for instance, I have a self-consistent system and I can add a new element to it. I can add something that expands it, a new rule, a new function that wasn't there before. And so if I'm choosing systems or adding to a system, I'm constructing a system, really, that requires intelligence. So evolution is an intelligent system. I'm taking the genetic code, or the system is taking the genetic code and is modifying that genetic code to match a goal. What's the goal? To reproduce. Okay. So we have the genetic code for a cell, and we have something that can add to that system, radiation, and just cause a genetic mutation. It might not be the best way, but it's a thing. And so it adds to it takes that self-consistent system and adds something or takes something away even. And then does that cell survive? Does that creature survive? If it does, then you keep on going. This process of evolution is an intelligent system. Here's another thing. Oftentimes, people say intelligence. Well, that means that this is going to be right. It's going to be right far more than others. No, it's the opposite. A function, a sort of a non-intelligent function, is right every time. So either it works or it doesn't. If it works, it's going to be consistent and work every time. An intelligent system is going to make mistakes. Matter of fact, maybe the hallmark of an intelligent system is that it makes mistakes. That evolution, there's a lot more failures in evolutions than triumphs. There's a lot more dead ends than successes. Um, so intelligence really doesn't mean better or faster or anything like that. It's just something that's required in situations where we don't have a function. Um, the analogy I give is you rather be driving down a road that's paved and has street signs and is marked than blazing your own trail. Sometimes you're lost in the woods and you have to blaze your own trail. And really, that's what intelligence is about. You don't want to use this. If there's a nice paved road, you take the paved road. You don't go off by yourself um, trying to get someplace in a hurry, just off into the wilderness. You rather go down a paved road. And really, that's what a mathematical system is a nice paved road. Intelligence is when you don't have that. Um, and so usually you don't want to be in a situation where you need intelligence. And as I said, a computer or whatever, you don't want to be in that situation where you need intelligence, but that's sometimes all you got. So, talk about Charles Darwin here. Life is a product of evolution. So evolution is an intelligent system. So in that sort of very primitive sense, sort of the quanta of intelligence, the minimum of intelligence. That's what evolution is, and it's developed us. Um, the the problems with this is that well, there were a lot of dead ends, and this took a lot of time. This is not an efficient way of doing things. It's just the only way we got. So intelligence is not faster and better. It's meta math instead of computational mathematics or something you can do. And of course, I'm using mathematics. This can be also a non-mathematical system. GenX is non-mathematical system in a sense, but we can go and use mathematics to describe what's happening. So this is it's not faster or better, it's just different. Intelligence is simple and common, and a lot of times it's not what you think it is. It's not what you particularly want. So a tree could be intelligent, while a supercomputer does not. There's a good chance that people have written an intelligent program by mistake and ended up as something that just doesn't work right. So what is intelligence? Intelligence requires a complete system. As I said, mathematically complete. One of the ways I think of a complete system is that if you remove an item, since everything's interconnected to each other, if you remove an item, you can uh, replace that item. You can, remove the item out of the system and you can get what that item was. So for instance, Gödel talked about all of mathematics and assign numbers to each mathematical function, and some are prime numbers and some are composite numbers, and you could take one of those out and either it's a prime number you can get from the composites or composite you can get from the primes. System has hysteresis, meaning there's a memory. What has happened to it is somehow been recorded. A system has a goal outside of the system, as I said, with evolution, life, reproduction. Items can be added to the system, um, and the change system matches the past system and the goal. And so that's what I was talking about. A tree, you can have mechanical hysteresis in something, and if that's part of how a tree computates something, you could have a tree decision. And I'll continue more in part.